Now, writing dissociation reactions, you have to go from the compound before it dissociates and write down the aqueous version after it dissociates. And so starting with something like sodium chloride solid, which is a soluble salt, will dissociate completely because it is a strong electrolyte, and we will write one arrow, just one arrow. And then we break it apart into the ion. Now, it is very important that when you write these out as the ions, that you are writing out that it has a charge. If you recall, all your alkali metals in group 1 have a +1 charge, and all your halogens in group 7A have a -1 charge. It's very important that we have the charges, very important indeed. Also, once it's dissolved, we will say AQ for aqueous. That means that it is dissolved in water. Now, since I have one arrow, that one arrow means I'm going completely to the ions. There's nothing left of the original compound. So this is a strong electrolyte. So this is strong. And so we can write some more dissociation reactions. How about this one right here? Let's go with sodium sulfate. Sodium sulfate. You should be able to recognize that it's an SO4, makes it a sulfate. Now, when we write the products over here, we do not break up our polyatomic. Our sulfate is an SO4 2-. It's a polyatomic. Do not break up your polyatomics. The sodiums, there's 2 of them. Now, this does not come off as 2 sodiums together. They come off one at a time. So the first one comes off as a sodium plus, and then the second one comes off to make 2 sodiums. So whatever you do, we're not going to write down that like this. I've seen folks do this where they'll say Na2 plus. That doesn't work. You should never do that. It come off one at a time. And so we have the polyatomic that's attached to it, and that's the sulfate. And you must remember that it is a 2- charge up here. Now, if you forget that it's a 2- charge, and you remember that sodium is a +1 charge, well, if there's 2 sodiums at +1 apiece, and the total has to equal 0 for the net charge, then 2 minus 2 would give me 0. So 2 of the pluses minus 2 gives me the 0, so I know I have the right charges on my ions. How about like this one right here? This time I'm going to use an ammonium with a phosphate. So this is ammonium. Let's not forget we need our aqueuses up here. This is an ammonium phosphate. That's your ammonium ion, NH4. There's 3 of them. You know that if you have a polyatomic, you got more than one of them, you have to put it in parentheses, so there's 3 of them there. And that's a phosphate, that's a PO4. And it's a PO4 3-. 3-. How do I know that? Well, if you remember that the ammonium has a +1 charge, and there's 3 of them, then that's +3 minus 3 gives me 0. Or you can remember that, how did we get this 3 in the first place? We cross the charges, and we can uncross the charge. So that 3 would go up there as a -3, and there's a 1 implied here, up here as a plus. And so this is going to dissociate. Once again, each one of these ammoniums is going to come off one at a time. So you have 3 of them, 3 ammoniums. There you go. We got the 3 ammoniums, and now we have the phosphate that comes off as well. And that's a PO4 3-. Once again, making sure that we add an aqueous, indicating that this is all happening in water. Now, these are some strong examples. And really the thing that you've really got to be careful about is that the charges balance. There's 3 pluses, 3 minuses, there's 2 pluses, there's 2 minuses, there's 1 plus, there's 1 minus. You got to be very careful that charges balance to 0. You also have to be very careful about these quantities, these subscripts. If there's 2 here, that means I got 2 of them over here. Now, also keeping in mind that this 4 over here means there's 4 oxygens. It doesn't mean that 4 oxygens come off. Remember what I said. These polyatomics right here, these polyatomics don't dissociate the polyatomics. Keep them together as the particular polyatomic. This is another reason why it's very important that we memorize and continue to stay fresh on our polyatomic ions. Now, there are other kinds of electrolytes as well, and they're the kind that don't dissociate completely and are mostly molecules. An example of that would be hydrofluoric, and we have the double arrow there, and we're dissociating H plus F minus, and the HF actually is dissolved, but it's dissolved as the molecule. And so what we have over here is mostly HF and few ions over here. This is really the only way that we can indicate that we have a weak electrolyte is by putting a double arrow there, which means that as soon as we form the ion, it comes right back to the molecule. This is an example of a weak electrolyte. So this is weak, and it has that double arrow. And we can do some other things like, let's say, like ammonium hydroxide. It's also weak. And in this case, we have the ammonium polyatomic, and we have a hydroxide polyatomic. So it's going to dissociate into those two pieces. The charge on an NH4 ammonium is +1, and so we're going to get +1 and aqueous, plus the hydroxide, aqueous. Notice, just like what we did previously with the strong electrolytes, if we have polyatomic, we're not going to break them up. We're going to keep the polyatomic together with the appropriate charge that goes with each one of these. Ammonium has a +1 charge, the hydroxide has a -1 charge. They add up to 0. So both of these are examples of weak electrolytes when we're dissociating them. Water is very weak, and it will actually dissociate into the H plus OH minus. And of course, water is aqueous because it's dissolved in water, and a H plus and a OH minus are produced. The vast majority of water is just the water molecule. Every now and then one will break apart into an H plus and an OH minus. So these three examples right here are of weak electrolytes. All three of them are weak electrolytes. And once again, we're trying to be very careful that when we dissociate the electrolyte into its ions, that that the charges are going to add up to 0, and that if we have polyatomics, we better not break them up.